Hello, I almost didn't see you there, Professor. I'm just solving some nonlinear PDEs on normal computers, which is something we can do. Hopefully you're able to figure out how to do that on quantum computers. But that's not what I'm here to talk to you about today. Today I'm going to talk to you about quantum ghost imaging. Oh, not that type of ghost imaging. This term ghost imaging comes from a phrase used because we're able to image with photons that never actually interacted with the object, thus taking an image of a ghost. Of course, it's not an actual ghost, it's an image of the object, but we're taking advantage of quantum mechanics properties, quantum mechanical entanglement, in order to image with photons that never interacted with the object. So this is a complicated process that relies on a concept called parametric down conversion. So what parametric down conversion is you pump photons through a nonlinear medium such as a crystal, and the output is two identical photons known as the signal and idler photons. These photons are spatially entangled, which means they're entangled in their lateral position with respect to the plane of the crystal, and their transverse momentum, again with respect to the plane of the crystal. The Hamiltonian for this process is very complicated. I talk about it in my paper. It's difficult to see how it will create two different beams that are entangled. So for the purposes of this video and the paper too, I simplify the Hamiltonian such that the beam is already split. So the beam is already split. We have a state psi, and N1 and N2 could be the two different beams. And so the Hamiltonian for the parametric down conversion process is this. G is a coupling constant and alpha is the amplitude of the beam. When you act it on the state, A dagger and A are creation and annihilation operators, which are the same thing as raising and lowering operators. We learned about that this semester. So if you operate it on the state, you get a new state, which is a superposition entangled state. It's not you can't factorize it, so it's entangled, and it's a superposition state. And as you can clearly see, so this is the Hamiltonian for the lateral position of the photons. It would have a different one for the transverse momentum. So as you can see, when you measure the position of one photon, the other photon will have to have the same lateral position. And then if you did the same thing for momentum, it has a different Hamiltonian, such that if you measure the momentum of one photon, it has to have the opposite momentum. So that's how parametric down conversion works, and this has given rise to many experiments which try to use quantum imaging to create images with photons that never interact with the object. So now I'll go over an experiment I talk about in my paper over here. This experiment is one of the more famous quantum imaging experiments, and it was done by Gabriela Barreto Lemos and co-workers in 2014. So what we have here is we have a beam splitter here. This shows it's a beam splitter because the two different headphones go to two different crystals. These tubs over here are the two different crystals. So what happens is one goes into one crystal, and out comes two entangled photons, which are the idler and the signal photons. Only the idler photon goes through the object and interacts with the object. So the transmission information about the object is now held in an entangled state between this idler and the signal photons. So then the idler photon that interacted with the object is then sent through another crystal, and out comes another entangled pair, which are the idler and the signal photons here. The idler photon, which holds information about the object, is just completely neglected and discarded. And so the signal photons that are outputted from the two different crystals go into the camera or the photon counter, depending on what you use in your experiment, or what your experiment is doing. If you want to image like an actual object, you'd use a camera. If you're performing like a double slit experiment where you want to see the interference patterns, you just use photon counters. So what we have here, since the only photon that interacted with the object is completely discarded, we measure the signal photons that did not interact with the object. The reason why we have two different crystals and two different signal photons is to produce a higher resolution image. So what we have in the two different measurements is one we have constructive interference and the other we have destructive interference. This is clearly shown in a double slit experiment. It's also shown when they image a cardboard cutout of a cat to represent Schrodinger's cat. So when you sum the two interference patterns, you get the intensity profile of the beam, and when you subtract the two constructive and interference patterns, you get the image of Schrodinger's cat, high resolution of Schrodinger's cat. As you could imagine, this has many applications in today's society. The U.S. Military put a patent on a research group's, or gave a patent to a research group's quantum imaging technology recently. It would be very useful to image through turbulence in the air, which is exacerbated by winds and smoke. Also through cloudy water and jungle foliage, and even just around corners. It's also being implemented in the medical industry to take high-resolution images of X-rays. I hope you learned a lot from this video, and I hope you'll learn even more from my paper. Thanks for having a great class. You're a fun professor, and I enjoyed being in your class. See you later.